This is a survey on memory architectures using PCM and STT-RAM. In a computing system, the memory subsystem accounts for a significant part of the cost and power budget. Some studies have shown that main memory alone contributes as high as 30% of the power, which in turn contributes to operational cost. In recent years, the memory technology scaling is hitting its power and cost limit due to the intrinsic properties of CMOS-based SRAM and DRAM memory technologies. Hence, researchers are looking into possible replacements. PCM and STT memory are two among the expected replacements. The following table shows a comparison between the characteristics of SRAM, DRAM, PCM and STT-RAM. Because of these characteristics, PCM is considered as a good candidate for replacement of DRAM and STT-RAM as a good candidate for DRAM and SRAM. About phase change memory, it's a non-volatile memory that can switch between amorphous and crystalline states with the application of heat using electric pulses. The amorphous phase has low optical reflectivity and high electrical resistance, and the crystalline phase has high reflectivity and low resistance. This change in resistance is used to infer logic states. Though PCM is considered as a good candidate for DRAM replacement, there are certain limitations. They are access latencies, energy-intensive writes, and endurance. This slide shows the results when PCM was used as a replacement for DRAM in main memory. Actually, the application delay increased, energy consumption increased, and the average lifetime was just 177 days. Hence, it can be inferred that some architectural changes has to be made in order to use PCM as main memory. This slide lists some of the approaches to overcome the limitations of PCM to be used as main memory. The first method involves using a hybrid architecture consisting of a DRAM buffer in addition to the PCM memory. The prime motive is to reduce the number of writes to the PCM memory. When a page fault occurs, the page is fetched from hard disk and written into the DRAM only. This eliminates the overhead of writing the PCM every time a page fault occurs. As we know, the write latency of PCM is higher and also power hungry. Now, since we reduce the number of writes to PCM, it improves the performance and energy consumption. The second method is line level writes. In order to face the limitations of endurance in PCM, line level writes can be used. Usually, the data from the secondary storage will be read page by page and stored in the main memory. But if the data is written at the size of processor cache line instead of writing page by page, then changes can be tracked at the granularity of a cache line, and hence only dirty lines can be rewritten. The average lifetime was estimated to be 5.6 years when using partial write techniques. Next method is wire leveling. Most of the write operations are destined to a small subset of the memory space. Hence, there will be unbalanced write distribution. Hence, the cells which are written more frequently tend to fail sooner than others. For this reason, wire leveling algorithms are used. Wire leveling algorithms are used to distribute the write operations equally throughout the memory. Thus, increases the lifetime of PCM. Next method is to avoid redundant bit writes. Bulk of write operations are redundant, meaning these redundant write operations don't change the value of the PCM memory cell. For real workloads, single-level PCM cell MLC2, MLC4 had an average redundancy of 85%, 77% and 71% respectively. Hence, by exploiting this property of redundancy, when these redundant writes were removed, the lifetime of the memory increased by 4.5, 3.5, 3.0 times for SLC, MLC2, MLC4 on average. Now let's look into the STT-RAM and the possibility of using it as main memory and cache. The STT-RAM cell consists of a magnetic tunnel junction as the memory storage. An MTJ contains two ferromagnetic layers, free layer and fixed layer, and an oxide barrier layer in between. The fixed layer has a fixed magnetization direction, while the magnetization direction of the free layer can be altered by passing spin polarized current. If the two layers have different directions of magnetization, the resistance of the MTJ is high, representing logic 1, and vice versa. This slide shows the results of using STT-RAM as a direct replacement of DRAM in main memory. It can be seen that the performance degraded by 5%, while the energy consumption increased by 96%. Though there are no refresh cycles in STT-RAM, it's not enough to compensate for the energy loss during writes. Now, let's look into some of the approaches to improve the performance and energy of STT-RAM to be used as main memory. The first approach is to use an STT-RAM with DRAM buffer. When hybrid memory consisting of STT-RAM with DRAM buffer is used, just like suggested for PCM, there is a significant improvement in performance and energy consumption. Average performance of this architecture is 1% worse than DRAM. Regarding energy consumption, there was an improvement of 65% compared to STT-RAM only architecture, but it is still 35% worse than DRAM only architecture. Second approach is to use selective and partial writes. When row buffer conflict occurs, test results reveal that during more than 60% of the row conflicts, row buffers are clean, and only 6% of the conflicts have more than 3 dirty blocks. Selective writes will not write when the row buffer is clean. Partial writes will only write the dirty blocks of the row buffer. Simulation results show that using selective write in STT-only RAM improved the energy consumption from 196% to 108%, and partial writes improved it from 108% to 59% of DRAM. The next approach is to use smaller row buffers. It improves energy consumption. With increasing number of cores, the advantage of having large row buffer diminishes. Even for 1 KB row buffer, the row buffer heat rate is less than 50% for 8 core case when row interleaving is used, and less than 10% for block interleaving. Hence, having bigger row buffer is not energy efficient. But using smaller row buffers in DRAM is costly. Since STT-RAM has a non-destructive read, small row buffers can be used without additional area or complexity. Simulator results show that 64 bytes of row buffer in STT-RAM based memory showed 67% improvement of memory energy compared to the baseline DRAM configuration that had 1 KB as row buffer without degrading performance. Let's look into using STT-RAM as cache memory. Simulation results show that the performance of STT-RAM is almost the same as SRAM. Write access consumes more energy, but the static energy consumption is just 10% that of SRAM. Now, let's look into some of the approaches to improve the performance and energy of STT-RAM to be used as cache memory. Let's look into the first approach, early write termination. Evaluation of 16 MB STT-RAM L2 cache revealed that around 88% of the writes are redundant. Since write operation is the most energy consuming and time consuming operation in STT-RAM, avoiding such redundant writes improves the performance and energy. The next method is low bits cache. This method works based on the observation that upper half bits of words are not updated as often as lower half of the word. This method proposes a small SRAM cache in between L1 cache and STT-RAM L2 cache. This small SRAM cache stores lower half of every word stored in L2 cache. Simulation results of 2 MB L2 cache with 32 KB LBC gave an improvement in performance of 46%. The next approach is varying retention period. Reducing the retention period of STT-RAM improves the write access time and reduces write current, which in turn reduces dynamic energy. For L2 cache, it was estimated that 10 millisecond retention period is sufficient. Hence, reducing retention period can improve the performance and energy consumption. The next method is multi-level STT-RAM. Multi-level STT-RAM can store multiple bits in the same memory cell. Simulation results showed that a 16 MB MLC cache consumed 21% less energy and 30% less area than 16 MB SLC cache. The next approach is to use a hybrid cache consisting of L1 cache made of SRAM and L2 L3 caches made of STT-RAM. When pure SRAM based caches are compared with SRAM STT-RAM hybrid architecture, the hybrid architecture showed almost equal performance to pure SRAM, but it was much more energy efficient than SRAM only cache. In this presentation, we discussed about the various architecture and optimization methods for using PCM and STT-RAM as main memory and cache. There is a good possibility that these non-volatile memories are soon expected to replace SRAM and DRAM in memory subsystem, either completely or as a combination with them. These are the references used for the survey.